Hello everyone. Today we are going to be going through how to graph some sine and cos circular functions that have multiple transformations added to them. Let's begin by illustrating this concept with a cos graph, but note that the same steps can be applied to graphing a sine graph. Okay, let's begin. Say that we have a function h of x equals 3 cos of 2x plus pi on 3 plus 1. And we are graphing this h of x for the domain of 0 to 2 pi. The very first step that we have to do is first factorize out this coefficient of x over here. So first we factorize out any coefficients of x. The reason that we do this is so that we can see our transformations much more clearly before we begin our process of graphing. So our graph of h of x can now be rewritten as 3 cos of 2 brackets x plus pi on 6, all plus 1. Now over here, we can clearly see the transformations that have been done to our original graph of cos of x. We can see that there is a dilation of 3 from the x-axis. So we've got a dilation of 3 from our x-axis. We also have a dilation of a half from the y-axis over here. So we've got a dilation of 1/2 from the y-axis. Remembering that our coefficient of x is always our dilation from our y-axis, and we always have to take the inverse of our coefficient of x to find the factor of this dilation. So over here, there has been a dilation of factor 1/2 from the y-axis, not a dilation of factor 2 from the y-axis. So be very careful of that. We can also see that we have some translations over here. A translation of pi on 6 units to the left. So a translation of pi on 6 to the left, and a translation of 1 unit up. So a translation of 1 unit up. Now, you may be wondering, why is our translation in the x-axis pi on 6 units to the left rather than pi on 3 units to the left? Now, we need to remember that every time we have a coefficient out the front of our x, so every time that we have a dilation from our y-axis, this causes our period to compress or expand, and this in turn also determines or influences how our shifts or how our translations behave. So it is very important to first factorize out our coefficient of x so that we can clearly see our translation in the x-axis. So over here, we can clearly see that our translation is pi on 6 units to the left rather than pi on 3 units to the left. Okay, moving on. We always deal with our dilations first, so we're going to ignore our translations for the moment. If we are converting our usual graph of cos of x, so our usual graph of cos of x would look something like this. And over here we would have 2 pi, over here would be pi, over here would be pi on 2, and over here would be 3 pi on 2. Now if we begin to add our dilations to our usual graph of cos of x, we know that this dilation of 3 from the x-axis is actually causing our amplitude to change. Our amplitude is changing from 1 to 3. This means that our upper and lower bounds of this graph, so our highest y value and lowest y value of this graph, will now change from 1 and -1 to 3 and -3. We also know that this dilation of 1/2 from the y-axis will cause our period to decrease. This means that our period will now be divided by 1/2. So our period will go from 2 pi to 2 pi over 2, which just equals pi. Because we are graphing over a domain of 2 pi and 1 period is pi, we know that we will be graphing 2 periods of the graph within this domain. So this means from 0 to pi, there will be 1 period of this graph, and from pi to 2 pi, there will be another period of this graph. So if I am to draw our dilated graph, it should now look something like this. So over here, from 0 to pi, we have 1 cycle of the graph, or 1 period of the graph, and then from pi to 2 pi, we have another period of the graph. Okay, now that we've handled our dilations, we can move on to our slightly trickier translations. Let's begin with our translation of pi on 6 units to the left. Now at this stage, I recommend redrawing our dilated graph on a new set of axes to make things a little bit more clear. So let's do that now. Okay, now that we've got our dilated graph on a fresh set of axes, we can now look at our translation of pi on 6 units to the left. Now, I find that the best way to keep track of all of our turning points and all of our x-intercepts is by watching out for our turning points in particular. The reason that we refrain from labeling our x-intercepts at the moment is because when we apply our translation of 1 unit up, we can see that our x-intercepts may change. So let's refrain from labeling our x-intercepts at this stage. Instead, we can begin to label some of our turning points. So we know that this turning point will be at pi on 2, negative 3. This one is at pi 3. This one is at 3 pi on 2, negative 3. And over here, we have another one at 2 pi 3. Now, what we can do to visualize this shift of pi on 6 units to the left is first label these points on our graph. So we know that this turning point, which was previously at pi on 2, will now be shifted pi on 6 units to the left. So we will calculate the x-coordinates of our new turning point by taking pi on 2 and minusing pi on 6. So this would equal 3 pi minus pi over 6, and this would simplify to pi over 3. So this new turning point here will now be at pi on 3, negative 3. This turning point, we can do the exact same thing. So we will take our pi and minus pi on 6 units from this. So this should now equal 5 pi on 6. So this shift will take this turning point to 5 pi on 6, 3. Similarly, these 2 points would also shift, turning into 4 pi on 3, negative 3, and 11 pi on 6, 3. So if we redraw this graph with our shifted coordinates, it should look something like this. And from over here, it should come back down until it reaches 2 pi. Okay, now that we've dealt with our translation in the x-axis, we can deal with our translation 1 unit up. Now, just to make things a little bit neater, I'm going to graph this translated graph on a new set of axes. Okay, now that things are a little bit neater, we can once again take note of the fact that our upper bound and lower bound at the moment is at 3 and negative 3 respectively. So if we are translating 1 unit up, this means that our upper bounds and lower bounds, so our maximum y value and our minimum y values, will now shift up by 1 unit. So this will now turn into, so this 3 would now turn into a 4, and this negative 3 would now turn into a negative 2. So shifting this graph upwards, our x-coordinates of our turning points should remain in the exact same spaces, but the y-coordinates of our turning points would change. Similarly, this translation of 1 unit up will also cause some changes in our x-intercepts, as you can see over here. So have a look at the x-intercepts here, and then have a look at our x-intercepts when we shift the graph up. Some of the x-intercepts actually become closer together, so this is why we refrain from labeling our x-intercepts until the very end. Okay, if we draw this out with a translation 1 unit upwards, our turning points are still at the same x-coordinates, so our graph should look something like this. So if we go to label our turning points, the x-coordinates would remain the same, so this would still be pi on 3, but our y-coordinate would change to negative 2 over here. Similarly, this x-coordinate would remain the same, this would still be 5 pi over 6, but our y-coordinate would change to 4. This would be 4 pi on 3, negative 2. This would be 11 pi on 6, 4. Now we can also find the coordinates of our endpoints at this stage. We can simply do this by substituting x equals 0 for this coordinate and x equals 2 pi to find the y-coordinate for this endpoint. So let's start with x equals 0. This should give us 3 cos of 2 times 0 plus pi on 3 plus 1. The 3 cos of 2 times 0 plus pi on 3 is just 3 cos of pi on 3 plus 1, which should equal, using our exact values, 3 times a half plus 1, which simplifies to 5 over 2. So this endpoint coordinate here would be 0, 5 over 2. Let's do this with x equals 2 pi. So if we take x equals 2 pi, we would get 3 cos of 2 times 2 pi plus pi on 3 plus 1. So this would equal 3 cos of 4 pi plus pi on 3 plus 1. Now we know that if we add 4 pi units to any reference angle in the unit circle, we would end up at the exact same spot. So if we draw up our unit circle over here, and we have a reference angle of pi on 3 units, if we rotate this by 4 pi units, so 2 full rotations. So this is rotating by 2 pi units, and this is rotating by another 2 pi units. So it's rotating twice by 4 pi units, only to end up at the exact same spot that it was at before. So this means that our reference angle of pi on 3 would remain the same. So this can be simplified to 3 cos of simply pi on 3 plus 1. Simplifying this, we get 3 times a half plus 1, which simplifies to 5 over 2 as well. So this end coordinate, this endpoint over here, will be at 2 pi 5 over 2. Okay, all that's left to do now is label our x-intercepts. To find our x-intercepts, we make our equation equal 0. So this means that 3 cos of 2x plus pi on 3 plus 1 will equal 0. If we rearrange to get our cos term on its own, this would equal cos of 2 of x plus pi on 3 equals negative 1/3. Now, to learn how to solve equations such as these over the domain of 0 to 2 pi, feel free to check out my video on learning how to solve circular equations over non-standard domains. As always, let me know if you have any questions. Otherwise, I will see you next time.